ठीक है? Okay, good afternoon everyone. So we'll start with a new chapter. Uh, the name of the chapter is combined loading, but we are going to start with a topic called thin walled pressure vessels. Have you done this in your first year? There was a time when this used to be covered in the first year. You have done this? Okay, we'll still do it. Okay. Uh, the reason for repeating it is that when you did it in first year, you had not done transformation of stresses and strains. Okay, so maybe you only knew the formula, the sigma 1 is equal to PR by T and the sigma 2 is equal to PR by twice T. Do you remember this? Huh? But you did not do any stress transformation associated with this, nor any strain transformation. So the more interesting problems in the context of thin wall pressure vessels happens when we do these kinds of transformation of stress and strain together with some combined thing. Okay, so in a broader perspective, we are going to learn it. So was it done in all the sections of first year, thin wall pressure vessels? Do you remember first year BEM? There used to be a course. Huh? Okay, anyway, we'll cover it. So overall, the chapter is combined loading. And within it, the first thing that we are going to cover is thin wall pressure vessels. Now, first of all, regarding this combined loading, please understand that till now we have actually covered quite a lot of ground. First of all, we did torsion, then we did SFD BMD, then we went on to do flexure, then transverse shear. All of these things we have done. So you understand that in an actual engineering application, these things are not usually going to occur in isolation. Okay, in the most common scenario will be you will have a shaft on which there is torsion, there will be some kind of axial loading also. By the way, you have done axial loading also in the tutorial sheet 0. So all of these things, axial loading, torsion, flexure, shear, all of these things will occur together. So we will see how when they occur together, we have to consider them in a combined fashion. Okay, it is not just a case of just adding them up together. We have to be a little bit careful with that thing. Okay, now the first topic is this thin wall pressure vessels. You can think of it like a continuation of the stress and strain chapter, or just an application, the most immediate application of the stress and strain chapter. So this chapter is basically application oriented, very much application oriented. Okay, so we'll first start with this thin walled pressure vessels. Now some general philosophy, some general application kind of motivating discussion. So tell me, why do you think thin wall pressure vessels are important, or where these things are important? Some actual things which can be referred to as thin wall pressure vessels. Boilers, absolutely. Then? Sorry? Oil tankers. Okay, gas tanker. What is the most common of gas tanker that you know? CNG tanker is more common. LPG cylinder. This is the flavor of the day. Ask your parents. Okay, LPG cylinder. In the campus also we had a crisis going on. Okay, so LPG cylinder. So all of you have seen LPG cylinder, right? Huh? We are all from India only. Okay, so LPG cylinder. Now, what is the characteristic feature of this thin walled pressure vessel? As the name suggests, you have this vessel within which there is some kind of a pressurized fluid. Fluid can be a liquid and or a gas. Okay, this we all know. Now, there will be a significant amount of pressure acting on the walls from the inside. Okay, it could be in some scenarios that the pressure is acting from the outside. Okay, now the characteristic feature of these thin walled pressure vessels, as the name suggests, is the thin wall. Now, do you think in an absolute sense the wall of a LPG cylinder is very thin? It is not really thin. I mean, if I give you a piece of an LPG cylinder, cut it out and give it on your hand, you will not be able to bend it. It's not that thin. Okay, it's not a flimsy piece of material. However, it is thin compared to the dimensions of the vessel. Okay, what other example of thin walled pressure vessel do you know? You, LPG cylinder, there is a level of difference between you because you're not actually directly using it. Okay, you're reaping the benefits of it, but you're not actually utilizing it with your own hands. Sorry, thumbs up bottle. Okay, to a certain extent.
The diving gear has those tanks.
Diving gear has those oxygen cylinders. Oxygen cylinder, yes. But I think something more common than that. Balloons, yes, balloons. Balloons. Huh? Pressure cooker, yes. Pressure cooker, yes. Huh? Oven. What is it? Bubble. The bubble is like balloon only. Na? What about those deodorant canisters? Right? Or the perfume, okay, whatever, that you directly use, or at least supposed to use. So anyway, let's not get into that. So we have lots of examples of these thin walled pressure vessels from our day-to-day life. Um, think, is submarine a thin walled pressure vessel? Now, I don't know the dimensions of the walls of a submarine. Please try to find it out. Okay, so take it as a homework that ask ChatGPT or Claude or Google Gemini if submarines can be considered as thin walled pressure vessels. Okay, all right. Now we have to analyze these thin walled pressure vessels. Analyze means what? That in the wall, what kind of stresses are generated? This is what we want to find out. Okay, why do we want to find this out? Because if we do not find this out, you take it as granted that some engineer has built up your deodorant canister and it is not bursting, or the LPG cylinder is not bursting. But somebody in the first place had to design it, right? So towards that design consideration, we need to know what the values of the stresses are. Okay, there is no doubt about it. Okay, somebody has to sit down and have an estimate of the stresses. So given this much pressure, given this material, what kind of stresses will be developed? Okay, so this is what we want to find out, as simple as that. Now, there are two most common kinds of pressure vessel geometries that we come across. One of them is a cylindrical pressure vessel and the other is a spherical pressure vessel. By the way, have you gone to this road that just get outside Nalanda and just ride down this road and turn right? Okay, that huge building you see, the Sathi building. No, just these two buildings, huge buildings that you see now outside. This newly developed buildings, the Diamond Jubilee Complex. Huh? You've seen those buildings, right? So if you just ride down this road, okay, just follow this road. You guys don't go this road down too much, but you can go to Tech Market and also by this road. Okay. So if you go down that road beside the Sathi building, just beside the Sathi building outside, you will see some very green colored vessels outside the building. Okay, I don't exactly know what their purpose is, but they are pressure vessels. Okay, so please remind me someone to find that out from somebody. Okay, all right. Now, and those are, all of them are cylindrical pressure vessels. You'll see like huge things. Now, just to give you an idea of the dimensions we are talking about, the diameters of these thin walled pressure vessels, okay, so diameter can be as large as 1 meter, 2 meter diameter. Okay, just compare with your height. I am like 173 centimeters. Okay, so it is like my height, the diameter. Okay, you have smaller ones also, but this is, I mean, nothing uncommon. So let us say that we have this cylindrical pressure vessel like this. By the way, the ends, they will have a certain geometry. We are not going to talk about the ends, because the ends, how they are constructed, how they are designed, and their stress analysis, that is an entire history and geography by itself. Okay, very very complicated. We are not going to, we'll just sweep it under the carpet for now. Okay, but do know that people like actual engineers who get to work with these kinds of thin wall pressure vessels, so there is an entire category of engineering called boilers and pressure vessels. Okay, and you need to have a proper certification to be actually able to work. Now just because I am an IIT professor saying big big things in mechanical engineering, if I go to such a company, they will not allow me to work because I don't have that certification. Okay, all derivation and all these things in one side, but when it comes to the actual thing, I have to have that certification. So this is very very important. And I also want to point out, because we always do these mathematical derivations and get into this like algebra, calculus, trigonometry, all these things, let us have a little bit of perspective about this. See, thin wall pressure vessels are extremely dangerous things. Okay, they are like a basic, like a sitting explosive. It is only because we mechanical engineers design it very carefully that the accidents do not happen. And they have to be operated in a certain fashion, because of which you need the certification that these accidents do not happen. However, accidents did happen at one time. People's lives were lost, huge loss of property, huge loss of money happened. Not just in India, okay, in foreign countries also. Okay, so these kinds of massive catastrophic disasters happened. It is because of those things people have become so very careful. Okay, so people have learned their lessons by making mistakes. Now, in a real scenario, you won't have this thin walled pressure vessel just floating in air like this. You would have stands, proper fixtures, and everything. But for the sake of mathematical abstraction, we are just saying it like this. And where they are put, a lot of stress analysis goes into that also. But we are just abstracting that, all of that away. Okay, the simplest of scenario. And spherical pressure vessel, as simple as that. It's a spherical pressure vessel, just like that. The special thing, as I said, is the thinness of the wall. Here also the thinness of the wall. Okay. So what are you going to do? So you understand. So suppose this is the cylindrical pressure vessel, and this is the curved surface. On this curved surface, if we just cut out a little stress element, what are the kinds of stresses that are present within the plane of that element? This is the fundamental question which we ask ourselves. Okay. Now, the thing is very easy. Those of you who remember the derivation will probably remember it's just like 10-minute thing. But we have to appreciate certain things here. Can you get a new battery for this? Just turned red. So what we'll do is we'll first take the cylindrical pressure vessel case. And for that, what we'll do is we will consider a cutting plane like this, and we'll consider another cutting plane like this. Okay, so you will get out a cut like this, you'll get out a cut like this. Yes. Oh, thank you. In addition to this, we are also going to take another cut, which is like this. So, slicing through the diameter of this thing. Okay. So, the section that is going to get exposed will look like this. Okay. Now you understand that these are just imaginary cuts. We are not actually cutting it open. Inside it, there is the pressurized fluid. Okay, liquid, gas, whatever. There's a pressurized fluid. So in this cut thing that we have shown, this is the thought experiment. The fluid is still here. Okay, it's not as if it is coming out. Okay, so it's just a thought thing. Now, uh, in this thin wall, you are going to experience the stress. Just imagine what happens in a balloon. When you blow into the balloon, the membrane, it gets stretched. Okay, and there is a stress developed in that, and if it exceeds a certain amount, it bursts. Okay, in a similar fashion, this imagine that this thin wall is like the membrane of the pressure vessel. There is a technical difference, by the way, between a thin wall and a membrane. Okay, we'll not go into all those things. Okay, membrane basically cannot take any bending. Okay, it is like a string. It is like the two-dimensional counterpart of a string. uh, String cannot take any bending, right? A beam can take bending. Okay, so now in this part of the thin wall also you are going to get stress. Okay, so here you are going to get stress, here you are going to get stress. This much is all easy to understand in a very qualitative fashion. But now, uh, okay, let's do the derivation and then I'll start my the extra discussion that I want to have. So let's take it very simply that over here you are going to get these kinds of stresses. Here also these kinds of stresses. Okay, and here you are going to get something else, but we'll talk about that later. And over here in the inside, okay, please understand that this portion, this entire half cylinder, that is filled with the fluid. Okay, so if I just consider this plane, then what kind of forces are being exerted on that? You will have the force due to the pressure of the fluid, okay, which is the counterpart of it. So when you have cut it, there is another part which I have not shown. That part of the fluid is exerting pressure on this part. Okay, so it is like a free body diagram. So all over on this rectangular surface, you are experiencing this pressure. All right. If you have any problem, do ask me. Okay. Acha. Now we'll call this thing, this yellow colored thing, this is the sigma 1. This also is the sigma 1, and this is the pressure. This blue colored thing is the pressure. I don't know how much the camera is catching the colors, but at least you guys can see yellow and blue, right? Okay. Now this dimension, let's call this delta x. And over here, this much, this is the thickness T. Same here. This is the thickness T. So what is the force that is experienced by these thin walls? Sigma 1 into T into delta x. But there are two of them. Okay, so into 2. Now this thing should be balanced by the pressure. Okay, so what is the pressure? P into 2R. By the way, this is the 2R. Okay, this is the 2R. This is the 2R. 2R means the radius of the inner radius of the cylinder. This is very important. Okay, this is the inner radius. So R is the inner radius. P into twice R into delta x. Very good. And from this, what do we get? Sigma 1 is equal to PR divided by T. That's it. One formula done. Okay, that's it. Next, we are going to consider what happens over here, okay, on this thing. For that, we need to take a slightly different kind of cut, or maybe from here also you'll be able to get it. Forget about all the other cuts, just consider this one, okay, just this cut, forget about this cut, forget about that, this, all these cuts, we'll just consider this thing. Okay. Again, we'll have this fluid pressure. This is the P. And on that ring that is visible, we are going to get some stress. This will call as sigma 2. Okay. And again, we are going to do the force balance. So tell me, what is sigma 2, or what should I multiply with sigma 2 to get the force? Sigma 2 into twice pi r into T, and this should be equal to what? P into pi r square. So sigma 2 is equal to PR by twice T. This is another formula. Okay. Now, every time I have to do this, I get a little bit confused. Okay, especially within the pressure cooker situation of an examination hall. So sigma 1 is equal to PR by T and sigma 2 is equal to PR by twice T. Which one is what? Okay. Now you may think, okay, easy solution. Where there is 2, there is 2. Okay, easy way to remember. But then suppose you mistake that this was sigma 1 or that one was sigma 2. Which one was sigma 1 and which one was sigma 2? Okay, these things happen when you start studying like 36 hours before the examination. Okay, so what is the trick? So there is one small trick which should not go outside KGP, even though I'll upload this video. So you see this 2, okay, it looks a little bit like Z. Okay, it looks a little bit like Z. And Z is in this longitudinal direction. Therefore, please understand. Okay, I will not say anything more. Now, spherical. Okay. What do you do for spherical? Yes? You guys tell me. You have done, na? You tell me. Suppose this is not even a challenge. What am I asking you? Leave it. I'll do it myself. So suppose we just take a cut like this, okay? I'm going to ask you a challenging question just in a minute. So we get this thing. Okay, so again we have this sigma. This is the sigma, and you have this pressure here. So what do we have? Sigma into twice pi r into T, that is equal to P into pi r square. This is equal to, sigma is equal to PR by twice T. Okay. Now, this is not the challenging question. I'm just saying it for the sake of completeness. Does it really matter how I take this cutting plane? I take like this, whatever way I take, you are going to get this same calculation only, same derivation only. Okay. So in the case of a spherical vessel, uh, it is always this sigma is equal to PR by twice T. Okay. Now, the thing is, this sigma 1 is equal to PR by T and sigma 2 is equal to PR by twice T. I want to probe this a little bit deeper in a way which is not given in the textbooks. Meaning that what have we actually found out here? If I consider this, like if I come back to this original diagram and I take a look at a stress element, what kind of a stress element am I considering? I'm considering this kind of a stress element. Right? If I zoom into that, it will look like this. It will look like this. That sigma 1 is present where? Here. This is the sigma 1. Please convince yourself that this is so. This is the sigma 1 in the circumferential direction. Okay, so this is the circumferential direction along the ring. Okay, along the ring, or what is referred to as the hoop. Hoop is a ring. Okay, so along this hoop direction or the ring direction or the circumferential direction, you have the presence of this sigma 1. And what you have found out here, this sigma 2, this is in the longitudinal direction. Okay, so you have the sigma 2 over here. This is the sigma 2. Okay, now there are a number of subtleties involved here. Just think for half a minute and tell me, what do you think is missing in this picture? Like, you should have a suspicion that I am not telling you certain things. Sorry? Inside and outside pressure. So there must be some kind of a pressure from the inside, and of course there is a pressure. The entire thing is getting stressed because of that pressure which is acting from the inside. If that pressure were not there, nothing would be stressed. So definitely there is a pressure from the inside. Okay, why am I not drawing it? That is one question. Any other thing that you have regarding how this sigma 2 and sigma 1 I have drawn? Acha, let me just redraw it in a fashion which is more common to your eyes. I have drawn it in a slightly curved fashion. Suppose instead I draw it like this. Do you think anything is missing here? Very good, very good. So shear stress is missing. You also thought that. Okay. So shear stress is missing. Okay. Now you tell me, does that make sense? It is not a trivial question. Okay.
If the fluid is flowing in the pipe, then there would be stress.
Not quite. See, fluid is still not flowing. So Akshat is saying that if the fluid were flowing, then we would have the shear stress. Okay. But please note that these stresses are not on the wall. They are in the wall. Okay. They are in the wall. So the kind of shear stresses that you are thinking of, that would be there on the wall at the interface between the fluid and the solid. We are not talking about that location. We are talking about inside the wall. Okay, good. At least you appreciate that there is something to ponder about. So what is actually happening here is there is something deeper going on. So you see, what kind of a geometry is this? This cylindrical pressure vessel? Like purely from a geometrical consideration, it is a cylinder. Okay, what kind of a geometry is a cylinder? By the way, when we say a cylinder, you can also have an hexagonal cylinder. You can have a square cylinder also. So we should be very careful to say that it is a circular cylinder. Okay, it is a circular cylinder. Now, what kind of a geometry is a circular cylinder? So if you look into the cylinder, then what will it look like? It looks like a circle. Please accept that this is a circle. Okay. So in terms of your first year maths and maybe even before that, what kind of symmetry does it have? So, right. So say that loudly. Axisymmetry. Okay. So this is an axisymmetric geometry. So, very good. Okay. This is axisymmetry or axisymmetric. This is axisymmetric. Good. Axisymmetric means what in mathematical terms? So imagine that I have set up my coordinate axis using the r theta z coordinate system, meaning the cylindrical coordinate system. Then my z is pointing out of the board. My r is like this and my theta is like this. All of you agree? So this is my r theta z coordinate system. This is axisymmetric about the z axis. Okay, this we all understand. Now, the implication of axisymmetry is that this is the mathematical implication that the del theta of anything is equal to 0. In words, what it means is that there is no variation in the theta direction. So whether you sit here or here or here or here, with reference to the center, they are all equivalent positions. Okay. Let that sink in. Okay, this is extremely important all throughout your life, especially if you go into fluid mechanics or solid mechanics higher studies. This will be, and certainly in manufacturing also. So this is going to be an extremely important concept, that the del theta of anything is equal to 0 is what is actually implied by axisymmetry. Okay, so nothing should be a function of theta. Now, can you tell me that if we go back to the torsion chapter, okay, if we go back to the torsion chapter, I'll go to the rough column here. Rohit, please check if this is getting captured. Okay. So if we go back to the torsion chapter and we look at the cross section of a shaft, this we considered repeatedly. And what kind of loading was there on the shaft? You had this twisting kind of loading. Okay. We had this twisting kind of loading given by this torque T. Is this axisymmetric? You all agree, right? Does anyone not agree that this is axisymmetric? Please raise your hand confidently. Okay, this is very much axisymmetric. Okay, so the presence of a load in the theta direction does not preclude axisymmetry. Okay, it does not prevent from axisymmetry from happening. A presence of a load in the theta direction, as long as that load itself is not varying along the theta direction. Okay, meaning that suppose our twisting action was like this, that from here to here you were twisting it to a certain thing and then there was something else. the implication would be that there will be some kind of an angular acceleration also. Okay, so that is completely beyond the scope of these things. Okay, we are in the realm of statics. So this kind of a situation would still be axisymmetry. Now, do we have that kind of a twisting action in this thin walled pressure vessel? You have the thin walled pressure vessel like this, right? The fluid is exerting pressure in which direction? Sorry. You have the thin walled pressure vessel like this. Okay, so you do not have any twisting action. You only have the load acting radially from the inside in the radial direction. So that pressure is acting in the radial direction. Okay, now we understand that del theta of anything is equal to 0. Now, just by this, can we say that the deformation in the theta direction is 0? Forget about everything else. If I just tell you that del theta of anything equal to 0 because axisymmetry situation, from that can you conclude that the deformation in the theta direction is 0? No. Why not? Because you have this situation where the deformation in the theta direction is not 0. It is still axisymmetric. Here also you have del theta equal to 0. But here, because you have a loading in this twisting direction, in the theta direction, therefore you do not have any you do have some deformation in the theta direction. But here obviously do not have any deformation in the theta direction. Okay, because there is no load in the theta direction. Please be very careful about this. I'll pause for 15 seconds. You think about what I just said. In the case of the thin walled pressure vessel, we do not have any deformation in the theta direction. But in the case of torsion, we do very much have deformation in the theta direction. If you have any doubt about it, please ask. Okay, so maybe you will have your doubts later. Now, if we do not have any deformation in the theta direction, okay, then things do get simplified quite a bit. All right, you tell me one thing. If del theta of anything is equal to 0, and suppose I substitute over here any one of the displacement components. Here what I am referring to is the strain chapter. In the strain chapter, what kind of displacements we considered? We had the u vector. Okay, the displacement vector u. That u had the ux or the uvw components. That was with reference to the xyz coordinate system. If you choose to work with the r theta z coordinate system also, you are going to have corresponding uvw. U will be in the radial direction, v will be in the theta direction, and w will be in the longitudinal direction. Okay, I know I'm going a little bit fast here, but everything is getting recorded. So if I substitute w over here, w is the displacement in the longitudinal direction. Del w del theta will still be 0. You agree? Because I said anything del theta of anything is equal to 0. So if I put w, it will be 0. If I put u, it will be 0. And if I put v, that also will be equal to 0. However, we have just agreed that v itself is 0. V is what? V is the displacement in the theta direction. Okay, so I'll write that clearly over here. So v is equal to 0. I'll write it in a separate way. So because of axisymmetry, you have this, and no loading in the theta direction. This implies that v is equal to 0. V is the displacement in the theta direction. Please write this carefully. You may not appreciate this right now, but later on it will help you. Okay. As a result of these two conditions, okay, as a result of these two conditions, if you write out the different strain components in the r theta z system, then what will happen is that you are going to get epsilon r theta equal to 0 and epsilon z theta equal to 0. Okay, these two conditions together, they will imply this. Okay, both the condition of axisymmetry as well as the no loading in the theta direction combined, these two conditions combined will give you epsilon r theta equal to 0 and epsilon z theta equal to 0. Okay, please distribute the tutorial sheet 7. If you have epsilon r theta equal to 0 and epsilon z theta equal to 0, please note that from this epsilon z theta equal to 0, you are also going to get tau z theta equal to 0. Okay, fine. Now coming back to this picture, this 2 is in which direction? Very good. This is in the z direction. Okay, this is the z direction. What is this direction? This vertical direction? That is the theta direction. Very good. This is the theta direction. So the shear stress, which if I have to draw something like this, okay, if I have to draw something like this, which component of the shear stress is this? This is tau z theta. Okay, this is tau z theta. You see here epsilon z theta is equal to 0, because of which tau z theta equal to 0. What is the relation I am using here? This is the relation I am using here. Tau z theta is equal to twice g epsilon z theta. This is from the generalized Hooke's law. I told you this is going to be an application oriented chapter. Everything that we have learned till now will be applied here. So this is the thing. So this tau z theta is turning out to be 0. This is why I did not draw the shear stress. Okay. This tau z theta equal to 0 means that the tau theta z that you have over here, that also is 0. Okay, because tau z theta is equal to tau theta z. Okay. So this thing, now the most natural question that should come to your mind is, all right, we have chosen to draw our stress element in this fashion, where the edges are oriented along the z and theta. But suppose we chose our stress element not like this, rather we chose our stress element like this, in an oblique way. Then what? Then will there be shear stress? Everyone, please look at this question. In this thin walled pressure vessel, instead of a stress element which is oriented very nicely and aligned very nicely with the z and theta direction, instead of that, I take an element which is slightly rotated. Then on the edges of that element, are you going to get only normal stresses, or are you going to get shear stresses also? You will get shear stress. Okay, you will get shear stress. So this thing is actually not mentioned very clearly in Weir and Johnson. It's kind of implicitly understood that you'll understand it. Okay, so but you see there is so much thought into it. Okay. However, in the spherical pressure vessel case, you do not have any such complication, because it is perfectly spherically symmetric. No matter which way you look at it, it is always the normal stress. Okay, there is no shear stress there. You can think about it. All right. Now, I'll give you. First, let the tutorial sheet 7 be distributed. Rohit, please give me a sheet. Thank you. All of you, please take a look at this last question. I don't want you to do this problem, but I want you to look at the expression here. Question number 14. You see different expressions of the strains are given in the r theta coordinate system, not the r theta z coordinate system. These are the polar coordinate systems. Okay. This is the polar coordinate system here, the r theta. So here the epsilon r theta that you have, what you have, there is a half, then within bracket 1 by r del u del theta plus del v del r minus v by r. Okay. Just check whether what I said regarding the epsilon r theta being equal to 0, that holds true. From axisymmetry, you have del del theta of anything is equal to 0. That means that no matter what the value of the u is, you will have the del u del theta term equal to 0. The first term that is there in epsilon r theta, the del u del theta is equal to 0. The next two terms, del v del r minus v by r, those are also 0. Not following from axis symmetry, however, but following from the condition that you have no loading in the theta direction. The v itself is 0. Okay, the v itself is 0. Okay, so that is why I said the epsilon r theta over there, this epsilon r theta is equal to 0. Okay, there is a way to find out the epsilon z theta also. Okay, and when we find that out, you'll find that you'll get terms like del w del theta, that will be 0. Then there will be a term like del v del z, that will be also 0. That is how the epsilon z theta is 0. Okay, now we are not going to handle this tutorial sheet. Okay, today in the combined loading chapter, the thing is, more or less we have done all the theory. There is as such no new theory to be developed. You have done axial loading, you have done torsion, you have done flexure, you have done shear. Now you have to bring all of them together. So the thing that we'll do is we'll take up the problems from the tutorial sheet 8 and we'll start looking at them. Okay, so tutorial sheet 8. We'll give you a break, don't worry. Rohit, give me a. So please look at question number 5. There are 2 pages. Everyone has gotten a sheet? Okay. All right. Question number 5. The thin-walled cylindrical pressure vessel shown in the figure is subjected to an internal gauge pressure of 15 megapascal. Gauge pressure means what? Over and above the atmospheric pressure. Okay. So outside also there is a pressure. There is very much a pressure. Okay. So the pressure that we are writing here is over and above that atmospheric pressure. If the thickness is 10 millimeters and the material constants are Young's modulus is equal to 200 GPa and Poisson's ratio is 0.3, determine the increase in both the diameter and the length of the pressure vessel. By the way, can somebody help me with what is the length here? 3 meters and radius is 0.5 meters. Okay. So radius is equal to 0.5. 0.5 meters. Okay, not a small radius. Diameter is basically 1 meter, as I told you. Okay, diameter is 1 meter. And the length is 3 meters. Just imagine how big it is. Okay, so the length is 3 meters. And how much is the thickness? 10 millimeters. Okay, just think and appreciate this. 10 millimeters is how much? 1 centimeter. How much is 1 centimeter? Huh? How much is, show with your fingers. How much is 1 centimeter? Huh? Okay, really small. Okay. So, this really is a thin-walled pressure vessel. Okay. Now, we have to find out the increase in both the diameter and the length of the pressure vessel. Now, what should I do here? I want to find out the increase in the diameter. So, yes, I will have to bring in everything together. Okay. All my knowledge regarding the stress, the strain, okay, how I handle these things, everything has to be brought in. Now, the change in the diameter, it is associated with which strain? You have what? The Z direction, the radial direction, the R direction, and the theta direction. My question is the change in the diameter is associated with the radial direction or the longitudinal direction or the theta direction? Radial direction, right? See how confident you are. Okay, I will do it in a certain fashion and then you say that how does it compare with what the picture is there in your head. Okay, we are not going to consider the epsilon r, we are going to consider the epsilon theta. Okay, let me write it, then you will see what is happening. Epsilon theta theta. Now epsilon theta theta, I will after all express it in terms of the stresses. But for now, I want to write it in terms of the change in length over the original length. So this should be what? Twice pi r plus delta r minus twice pi r divided by twice pi r. So what have I done? I have considered the length of the circumference. As the pressure vessel is getting pressurized from the inside, it will have a tendency to increase its diameter. Increasing in the diameter means that the length of the circumference is increasing. This is the new length of the circumference. This is the old length of the circumference. This is the old length of the circumference. When we have this, then do I not get Okay, and from this, do I not get where d is the diameter? So the question was that what is the change in the diameter? Okay, so the change in the diameter I have just now proved to you that it is actually connected with the epsilon theta. Okay, this is a point which each and every one of your senior batches have had some confusion with. Okay,
So,
yes,
when we say that that 3D element which we had taught earlier, the circumferential stress will have a component along the radial direction. So that is why the
I'm coming to that. The radial pressure, what happens to it, we have not even considered. Okay, we have not even taken that. So now we have to connect this. Okay, we have to find out answer. So we have to connect these things to the pressure which is given. Some pressure is given, right? 15 megapascal. Okay. So how do we connect all of these things? Because the connection of the pressure is with the stress, not with the strain. Okay. So what we'll do is, first of all, we'll connect the epsilon theta theta with the stress. Again, using the generalized Hooke's law. Correct? This is the exact counterpart of what we had in the XYZ coordinate system. Meaning that if I wanted to write the epsilon yy, that would be 1 by E sigma yy minus nu sigma xx plus sigma zz. Exactly in that fashion I am writing it. Now you tell me, what is this sigma theta theta? Is it the sigma 1 or the sigma 2? Sigma 1. This is the sigma 1. Okay. What is this sigma z? This is sigma 2. And what is the sigma r? We still don't know. What you know, you say confidently. How much is it? Sigma r? Yeah, that we know, it is the pressure. Okay, so my question is sigma r is equal to P or something else? Last chance. Think carefully. So suppose see, this is the inside of my pressure vessel. This is my hand. Look at my hand. Okay, this is the inside of my pressure vessel. Okay. So the radial direction is like what? Radial direction is like this. So if I look at the outside, this is the r direction pointing out of this. Here pointing out is what? Like this. The sigma rr here is like this. So sigma rr is equal to minus p. Okay, minus p. So this is minus p. What is sigma 1? This is equal to pr by t. Sigma 2 is equal to pr by twice t. Okay, so now you just compare. How much is r by t here? R is 0.5 meters, t is 10 millimeters. So that means 0.01. Okay, 0.01. So that is 0.5 divided by 0.01. Huge number. This p sitting alone. Okay, this one also there is a 2, but still a huge number. Okay, so everyone listen very carefully. Last bench, please. Excuse me. Please listen to this very carefully. So PR by T, this is a huge number. PR by twice T, smaller than this, but still a huge number. But P is a small number. And we are going to neglect this P. Now you see what kind of a unfairness there is. The whole game is being initiated by this bichara P. If there was no P, there would not have been any stress. And when it is coming to the question of finding out the stress, we are dropping that P. Okay, like the whole family is celebrating and the mother is being thrown out. It is like that only, na? Mother gave birth to all the children, then throw her out. This is like that. Okay, what to do? Cruel engineers. Okay, calculation easy हो जाता है, इसलिए करते हैं. Okay, so we'll drop it. Okay, we'll put a little sad face here. Okay, but now the calculation becomes easy. So effectively, what you are going to do is this. Okay, the value of E is given, value of P is given, R is given, T is given. You find out the epsilon theta theta and use that to find out the this thing. Find out the answer quickly. Do the calculation, please, and then you can take your break. Got it? Anyone? So we are basically going to have a 3-hour long tutorial for this chapter. First hour was for thin wall pressure vessel explanation. Rest of the 3 hours is for problems. Is anyone getting the answer? Getting? Arey bolo na. Okay, so take a break. One of you is getting, it's okay.